All right, so tonight let's pick up with the chemical reactions of triacylglycerol. So remember, your triacylglycerols are essentially your triesters that are made from glycerol, which is a trihydroxy alcohol, and three fatty acids. And the three fatty acids that you can use to make a triacylglycerol may be the same or they may be different. So the first reaction we'll take a look at is hydrogenation. So where did we see hydrogenation previously? We saw hydrogenation previously when we talked about the conversion of alkenes and alkynes to alkanes, where we added hydrogen to break the carbons of the double or the triple, or to break the double and triple bonds and convert them into single bonds. This is going to basically relate to alkene hydrogenation, where essentially the double bond will become a single bond and you add one hydrogen to each former double bond carbon. Because as you know, your unsaturated fatty acids contain one or more carbon to carbon double bonds. So hydrogenation converts the carbon to carbon double bonds of the fatty acid portions of triacylglycerols into single bonds. Okay. Now, essentially, the hydrogenation can be partial, or it could be complete. So in other words, when the hydrogenation is partial, that means that not all of the carbon to carbon double bonds are converted into carbon to carbon single bonds. When the hydrogenation is complete, that means every carbon to carbon double bond that's present is converted into a single bond. We talked about in the notes how commercially, things are partially hydrogenated, making products like margarine and such like that. For our purposes, for the reactions, we're essentially only going to focus in on complete hydrogenation. So example that you had in the notes and the homework talk, and the one that we'll do here in a moment, we'll focus on breaking all of the carbon to carbon double bonds that are present. We're not going to do partial, because in reality, if you do partial, how do you know what double bonds are going to be broken? And usually that leads to a lot of different isomers that could result. All right. So let's take a look at an example. And as you know from the homework, this will take a little bit to draw. Well, let's see. So let's do this one. CH27, 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 and then CH double bond CH, CH2, CH double bond CH, CH24, CH3, CH double bond CH, CH2, CH double bond CH, CH24, CH3, and CH double bond CH, CH2, CH double bond CH, CH24, CH3. And let's react this with 6 equivalents of hydrogen. And essentially the reason why I'm reacting this with 6 equivalents of hydrogen is because, as I said, we're going to do examples where the hydrogenation is going to be complete. And here, if you add up all the double bonds that are present, there are 6 double bonds that are present. So we want to break all of them. Okay. Essentially, the triacylglycerol remains intact. And that's one of the main differences between hydrogenation and the other 2 reactions that you saw and that we'll talk about very briefly. So, not very briefly, but we'll talk about briefly in a couple of minutes. That's essentially what I meant. But essentially, the triacylglycerol does remain intact. And everything is going to stay the same except for around the carbons of the double bond. So for each of them, and I'll start with the quote unquote top row first, the double bond between the carbons is going to become a single bond. I'm going to add hydrogen to one former double bond carbon and hydrogen to the other former double bond carbon. And then I would continue until I get to my next carbon to carbon double bond, where again the double would become a single, and I add one hydrogen to one former double bond carbon, the other hydrogen to the other former double bond carbon. And then I would complete the rest of the quote unquote row. Now, one of the things that you might notice or might have noticed when you were doing this is that when we add these hydrogens, these CHs are essentially becoming CH2s. So if you wanted to write them as CH2s, that's perfectly okay. The other thing you might realize is that if you recognize these as CH2s, then in this case, after the C double bond O, after the reaction occurs, then essentially you have 7, 8, 9, 10, 11, 12, 16 consecutive CH2s before you get to the other CH3. So if you wanted to write C double bond O, CH2 16, and then CH3, that would actually be perfectly acceptable as well. But my suggestion would be to draw it out. All right. So let's continue on. CH, we come across a double bond, becomes a single bond, add one hydrogen to each former double bond carbon, come across another double bond, add hydrogen to each former double bond carbon. So that would take care of my second quote unquote row. And then I come across another double bond, add one hydrogen to each carbon, CH2, come across my final double bond, add a hydrogen to each former double bond carbon, and then complete the rest of the structure. Okay. And essentially that would be the product that you would have here, where we've converted all the carbon to carbon double bonds in the triacylglycerol into carbon to carbon single bonds. Okay. So that's essentially how you draw the product of hydrogenation. Okay. So the next reaction we came across was acid hydrolysis. So what could we liken this back to? Well, essentially, we can liken this back to acid hydrolysis of an ester. Because remember, your triacylglycerols are triesters. Now, when we did the acid hydrolysis of an ester, remember the products were a carboxylic acid and an alcohol. Here, the alcohol is always going to be the same. The alcohol we're always going to get is going to be glycerol. And instead of getting back one carboxylic acid, instead, we're going to get back 3 fatty acids, which might be the same, or they may be different depending on the structure of the triacylglycerol. Okay. So let's take a look at an example. So we're going to react this with 3 equivalents of water and under acidic conditions. And the only reason why I'm going in the downwards direction is because on my drawing tool, I run out of space. So that's the only reason why I'm going in the downwards direction. All right. So how would we draw the products of acid hydrolysis of a triacylglycerol? Well, first off, where does the triacylglycerol split? If you remember back to our discussion of esters, we talked about the key bond for an ester, which was the bond between the C double bond O carbon and the alcohol oxygen. It is going to be at those 3 bonds, because if you look at a triacylglycerol, you have 3 ester groups. It's going to be at those 3 bonds where the triacylglycerol is going to split apart. And where are those three bonds? They're here, here, and here. Okay, because again, that would be the bond that's made when you would react each of these fatty acids with glycerol itself. Remember, when we talked about esters, the key bond is the bond that forms when esters are made. And as we saw, that is the bond that breaks when esters split apart. So essentially in these regions here is where the triacylglycerol would split. Okay. So if you think about the three equivalents of water, do we want to draw all three out? No. Each alcohol oxygen of glycerol would pick up a hydrogen from water. Because if you have three waters, you have HOH, H and OH, and H and OH. So each one of those oxygens separately is going to pick up a hydrogen from water. When they do, you end up with something that looks like the following. And of course, what alcohol is that? That alcohol, of course, is glycerol. Okay. And then each of the C double bond O carbons pick up what from water? They pick up the OHs. So once, twice, three times. So that each of the C double bond O carbons are going to become attached to OH to give us what? To give us the three fatty acids. Now, in this case, the three fatty acids that we get, are they going to be the same or are they going to be different? All three of them are actually going to be different. And you can tell just by looking at the fatty acid portion of the triacylglycerol itself. So we would draw them. So I'd start with my C double bond O for the first fatty acid, connect that to an OH, and then complete the rest of the structure. CH212, CH3. That's my first fatty acid. Second one, C double bond O, connects to OH, and then I have the rest of the structure. CH27, CH double bond CH, CH25, CH3. One thing to notice here is that I didn't break the double bond between the carbons. You know, in acid hydrolysis, it's the ester bonds that are broken, not the carbon-to-carbon double bonds that are broken. So the carbon-to-carbon double bond, whether you had one or more of them, they're going to remain exactly intact. Okay. And then for my third fatty acid, I'd have C double bond O, which is going to connect to OH. And that C double bond O carbon is going to be connected to CH214, connected to CH3. So for this example here, that would be the three fatty acids that I would get. Okay. So your acid hydrolysis of a triacylglycerol gives glycerol and three fatty acids. Okay. The third reaction that we took a look at was base hydrolysis of a triacylglycerol. So again, what can we liken this back to? We can liken this back to our discussion of esters. Now, when we talked about esters and their base hydrolysis, we talked about the fact that you get an alcohol, but instead of getting a carboxylic acid, you get, at the end of the day, a carboxylic acid salt. And we spoke about the fact that the reaction initially generates a carboxylic acid, but a carboxylic acid was not one of the final products because you can't have an acid under basic conditions. And what happens to a carboxylic acid under basic conditions? It becomes converted to a carboxylic acid salt. Very similar type of process here. Initially, we get three fatty acids. So essentially, the OH groups from the base, because we're going to be using three equivalents of base, replace the glycerol portion of the triacylglycerol. Essentially, just like we saw in what? Just like we saw in acid hydrolysis. And what is that going to give us? That's going to give us 3 fatty acids. But the same thing holds true. You can't have a fatty acid under basic conditions. What happens to a fatty acid under basic conditions? It gets converted into a fatty acid salt. And as you saw in the lab portion, and we mentioned it in the lecture notes as well, essentially the 3 fatty acid salts that form from the base hydrolysis of a triacylglycerol are commonly known as soap. So the fancy term for base hydrolysis of a triacylglycerol is saponification or soap making. That essentially is the fancy term for it. All right. So with this being said, let's take a look at an example. So let's do the following. All right. And let's react this with 3 equivalents of sodium hydroxide. Okay. So a couple things as we get the reaction going. First off, where's the triacylglycerol going to split apart? The triacylglycerol is going to split apart between the C double bond O carbons and the glycerol oxygens. And then the other thing is that we're not going to think about the NaOHs as NaOH. We're going to think about them as Na plus and OH minus. And again, because we're using 3 equivalents, there's going to be 3 Na pluses that are present, and there are going to be 3 OH minuses that are present. Now, as I talked about in the notes, and what you'll see me do here, is that I recommend, just like we did with esters, drawing the 3 fatty acids that initially form. So I'm going to do some side work. Now, for the 3 fatty acids that initially form, are they all going to be different? Are they all going to be the same? Well, they're not all going to be the same, and they're not all going to be different. 2 of them are going to turn out to be the same, and the third one is going to be different. Now, you could draw all 3 of them out, but what you could also do is that for the 2 that are the same, what I would do is just put a 2 out in front to remind yourself that you have 2 of them. And then we can translate that into the product as well. So initially, the OH groups of the base are going to take the place of the glycerol portion of the triacylglycerol to give us 3 fatty acids. 2 of them, you'll have C double bond O connected to OH, and then that C double bond O carbon will be connected to CH2, 16, and then CH3. The other one, the C double bond O carbon will connect to OH, and then you'll have CH27, CH double bond CH, CH2, CH double bond CH, CH24, CH3. Again, notice that the double bonds are not broken. The double bonds are going to remain intact. So that's absolutely going to be the case. Okay. Now, as we know, we can't have a carboxylic acid. We can't have a fatty acid under basic conditions. Just like we talked about previously, what part of a fatty acid, in other words, what part of a carboxylic acid is going to be lost under basic conditions? It's going to be the hydrogens of the carboxyl groups. Those 3 hydrogens, one by one, are going to be picked up by the alcohol oxygens of glycerol. So one of the products that we're going to get is an alcohol, and specifically, that alcohol is always going to be glycerol. Now, what happens to the fatty acids? Well, for the three of them, instead of the C double bond O carbons being connected to OH, instead, the C double bond O carbons are going to be connected to O minus. And what else is present that's going to be attracted to those O minuses? We're going to have Na plus. And remember, what type of bond do you have between the O minuses and the Na pluses? You have an ionic bond. So don't forget, don't draw a dash between them. Now, for two of them, after the C double bond O carbon, I have CH2 16 times in a row, and then I have CH3. You could draw that twice, or out in front of it, just put a 2. And that indicates to me, it would indicate to really anybody looking at it, that you have 2 of those fatty acid salts here. And then the other one, after the C double bond O carbon, we'd have CH2 7, CH double bond CH, CH2, CH double bond CH, CH2 4 times, and then CH3. That would be the other fatty acid salt that would result in this example. Okay. So as I mentioned, the nice part about these 3 reactions is that they are reactions that we have seen previously. So hopefully there's a bit of familiarity with them, but now we have to take it to sort of another level, especially with the acid and base hydrolysis, because we're getting a multitude of products from them. You know, glycerol and either 3 fatty acids or glycerol and 3 fatty acid salts, depending on whether it's acid or base hydrolysis. All right. All right. So the last 2 types of lipids that are ester-like fall under the category of what are known as phospholipids. The first type are what are known as glycerophospholipids. So one of the ways to explain them is when you think about a triacylglycerol. You know, I like to think about the glycerol portion as the backbone of the structure. And then as we know, attached to each of the oxygens of glycerol, you're going to have your fatty acids. So once, twice, and 3 times. How does that compare to what would be classified as a glycerophospholipid? We still have the glycerol backbone attached to 2 of the oxygens of glycerol. You're going to have fatty acids, which can be the same or they can be different. But the difference is that we're not going to have a 3rd fatty acid connected to the glycerol. Instead, the glycerol is going to be connected to a phosphate group, and that phosphate group is going to be connected to an amino alcohol. And as we'll describe this evening, and we talked about in the notes as well, the linkage that connects the glycerol to the phosphate to the amino alcohol is what is known as a phosphodiester bond. And hopefully we'll be able to further clarify that for you this evening. Phosphate, PO4. You know, it's a common anion in a sense, but essentially your phosphate is your PO4. The amino alcohols, usually, you know, I don't have you memorize a lot of structures, but as we saw in the notes, And as we'll talk about, the way that glycerophospholipids are classified is based on the amino alcohol that's present. So you really have to be able to recognize the structures of the amino alcohols. And there's three of them. The first, of course, is choline. So we'll refresh our memories. Choline has the following structure. And the term sort of amino alcohol represents the fact that you have an alcohol functionality, and then you also have an amine type functionality. The other interesting thing, and you'll see this in the way we draw the structures, is that in the body, you find amino alcohols having an atom or even atoms that have charges associated with them. They exist in an ionized state in the body. And that's important because, as you saw and we'll discuss, that influences their solubility in water. The second one is a compound known as serine. Serine is not only an amino alcohol, serine is also an amino acid. We're going to talk about those in a little bit. Okay. So serine is not only an amino alcohol, it's also an amino acid. And then finally, the third one you come across is what is known as ethanolamine. For ethanolamine, you have OH connected to CH2, connected to CH2, connected to NH3, and that didn't come out so well, so let me redraw. Right. So for ethanolamine, you have OH connected to CH2, connected to CH2, connected to NH3. So in order to identify the two types of glycerophospholipids that we're about to discuss with you, you have to be able to recognize the amino alcohol. So in this case, I am going to ask you to remember these structures. However, for triacylglycerols, if I give you the three fatty acids, you should be able to put together the structure of a triacylglycerol. I'm not going to ask you to put together the structure of a glycerophospholipid. But if I give you the structure of a glycerophospholipid, you should be able to classify it. So, what are the two types of glycerophospholipids? The first type, are what are known as lecithins. What defines a glycerophospholipid as a lecithin? They contain choline as the amino alcohol component. So let me give you an example. And I'm going to draw it a little bit more like how the textbook has it. And you'll see what I mean in a moment. And I always hope I leave myself enough room. A little bit better. So that N is going to be bonded to another CH3. Okay. So the reason why I'm drawing it this way is we want to illustrate the following aspects of glycerophospholipids, including lecithins, and even in a moment when we talk about cephalins. So it turns out that glycerophospholipids contain both polar and nonpolar regions. So the polar region is what is known as the head of a glycerophospholipid. And what is it? It's the phosphate and amino alcohol portion. So this portion out over here, in this area, is what is known as the head. Now, why is it classified as a polar region? It's classified as a polar region because you have atoms that have actual charges. Not only do you have the N plus of the, and I think I left that in oxygen, sorry. Yeah, I did. So let me just fix it. There should be an oxygen in between here as well. I thought I was one oxygen short of a phosphate, and I was. That would be CH2, and there should be an O. All right, that's better. So not only do you have the nitrogen with the positive charge from the amino alcohol, but then you also have an O minus as part of the phosphate group. So you have atoms that have charges. That's an ionized or polar region. The significance of that is that this region will dissolve in water. Now remember, the commonality that really brings lipids together as a whole is their general insolubility in water. Waxes, fats, oils, essentially are insoluble in water. Glycerophospholipids are sort of the one type of lipid that you come across. So one of the few types of lipids that you come across, because I think even the other type of glycerophospholipid, your sphingomyelin, which should have some water solubility as well, but they do show some glycerophospholipids do show some solubility in water, because the head is basically ionized or polar, and based on the idea of like dissolves like, that region is going to be able to dissolve in water. Now, the nonpolar regions, they are what are known as the tails. And essentially, those are the carbon chains of the fatty acids. So these regions over here would essentially be the tails of a glycerophospholipid. Now, these tails do not dissolve in water, but they can dissolve other types of lipids. So I can write that a little clearer. The question is why? Well, as we mentioned, most of the other types of lipids are what? Most of the other types of lipids are nonpolar. So again, based on the idea of like dissolves like, the tails won't dissolve in water, but other types of lipids will. But the tails come along for the ride in water because the head dissolves, and even though the tail doesn't dissolve, the tail's going to come along for the ride because the tails are still attached to the head. So it's like the legs in a sense. You know, if you're doing the swimming with your arms as the head, your legs are the tails, assuming you're not kicking, but they're coming along for the ride anyway. And as you saw in the notes, glycerophospholipids are highly involved in what? Lipid transport in the body, because body is composed of an aqueous solution. And, you know, so therefore the body is mostly composed of water. So how do we transport lipids? Well, we make, as we saw in the notes, these lipoproteins. And on the one of the things you have on the outside, on the surface of a lipoprotein, are the heads of the glycerophospholipids. They go into the water. And then on the inner core, you have your fats, your oils basically protected from water on the surface, but moving as part of a lipoprotein. All right. All right. You look at the amino alcohol, you got to be able to recognize it as choline, and therefore you have a lecithin. I'll mention the other thing on the next slide because this one's getting a little bit crowded. All right. So the other thing, the other type of glycerophospholipid to talk about are what are known as cephalins. Essentially, cephalins contain ethanolamine, and on occasion, I don't think too often, but on occasion, you see them contain serine. So let's show you an example. Okay. So if we look at the structure here, we recognize it as a triacylglycerol. We look at the amino alcohol component, and what amino alcohol does that look like? That amino alcohol looks like ethanolamine. So once you recognize that, you recognize this glycerophospholipid as a cephalin. Now, we talked about the fact that the linkage between what links the glycerol, the phosphate, and the amino alcohol is what is known as a phosphodiester bond. So what does that look like? Essentially, it looks like the following. Okay. If you think about esters, right? For an ester, we know that you have C double bond O connected to OC. Well, similar to that, there are what are known as phosphate esters. And for a phosphate ester, instead of having C double bond O connected to OC, you have P double bond O connected to OC. For a phosphodiester bond, a P double bond O group is simultaneously involved in two ester linkages. P double bond O OC once, P double bond O OC twice. So if you look at the cephalin, and you would find this in the lecithin as well, right here, P double bond O OC once, P double bond O OC twice. Glycerol, phosphate, amino alcohol. That linkage that you have there that connects them all together is a phosphodiester bond. And in fact, when you start to look through the notes in chapter 17, dealing with nucleic acids, you're going to come across phosphodiester bonds again. In fact, we'll see them in the other type of, I believe we're going to see them in the other type of phospholipid as well. Yeah, it's definitely there. But you're going to see them again in chapter 17 with nucleic acids also. Okay, so glycerophospholipids are your one type of phospholipid. The other type of phospholipid are what are known as sphingomyelin. The biggest difference here is that essentially the backbone is a compound known as sphingosine. Don't have to memorize the structure of sphingosine. You should be able to recognize it, and we'll give it to you here. I actually have to check back just to make sure I'm going to get it right as well. CH2NH2, and then CH2, sorry, too many hydrogens on the middle carbon. And CH2OH. So instead of having glycerol as the backbone of the structure, you have sphingosine as the backbone of the structure. Now, essentially the top portion actually doesn't react when you're forming a sphingomyelin. The middle portion here reacts with a fatty acid to form an amide group. And remember, we talked about amides previously. For your amides, essentially, you have C double bond O connected to nitrogen. So C double bond O connected to nitrogen, you have your amide. And then the OH portion combines with phosphate and either choline or ethanolamine in a phosphodiester bond. Just like essentially a glycerol phospholipid does with that third sort of OH in glycerol. So this is sort of the similarity that you have. So in terms of a sphingomyelin, you have something that looks like the following. Yep. Double bond too soon. CH212, CH3, CHNH, C double bond O, CH210, CH3, CH2OP, double bond O, O minus, O, CH2, CH2, NH3. All right. So again, wouldn't ask you to draw a structure of a sphingomyelin, but if you look at this compound and I ask you what type of lipid that it is, you should absolutely be able to identify it as a sphingomyelin. That's a definite expectation of what you should be able to do. Notice here, C double bond O connected to nitrogen. That's your amide portion. And then, of course, down here, you have your phosphodiester bond. And again, that region being ionized should be able to dissolve and interact with water. I don't know if sphingomyelin are mentioned as much in terms of lipid transport. They have other functionalities, like essentially preventing multiple sclerosis from occurring. So, they have their function as well. All right. So for sphingomyelin, you look at the structure, should be able to recognize it as a sphingomyelin. All right. All right. Last thing about lipids we'll talk about, and then we'll switch gears to amino acids, are your steroids. So steroids are essentially the one type of lipid that are not quote unquote esters. They are identified by having the steroid nucleus. So what does the steroid nucleus look like? The steroid nucleus looks like the following. Right? So one of the things I always drive home is that you can't miss the structure of a steroid. There's really not much else that has that nucleus associated with it, especially in the world of lipids. They're very easily identifiable. It's an example of what is known as a fused ring system. So what essentially does that mean? It means that you have rings here that have a common side, or they have overlapping sides. They share a side. So if you remember the way we designate the rings as A, B, C, and D, going from left to right, the A ring and the B ring share this side right here. That side is common to both rings. The B ring and the C ring share this side right here. It's common to both rings. And then the C ring and the D ring share that side right there. It's common to both rings. Okay. So essentially for a fused ring system, you have rings that have a common side or they have an overlapping side with each other. With the steroids, you don't have to memorize them. I'm not going to say draw cholesterol or draw testosterone or progesterone or anything like that. The main idea with the steroids, again, is just to be able to look at the structure and be able to identify it as a steroid. That's going to be one of the more important things to do. Should know a little bit about cholesterol, like we talked about, cholesterol esters, know a little bit about bile salts and such like that, but really not going to go crazy into saying, not going to say draw progesterone or testosterone or anything along those lines. All right. So that brings us to, I think, what I wanted to talk about in terms of lipids. All right. So let's get into chapter 16. All right. First big part of chapter 16 deals with amino acids. Why? Because later on in the chapter, we talked about proteins and enzymes. And as you saw, and as we'll talk about tonight, both your proteins and your enzymes are composed of amino acids. Okay. So all 20 of the amino acids found in proteins have essentially the same general structure. You have a central carbon, and attached to the central carbon, you have 4 things. You have what is known as an amino group. And sometimes in organic chemistry, when you specify an amino group, amino essentially has the form of NH2. Right? So that essentially is the amino group. Next, attached to the central carbon, you have a carboxyl group. And of course, where do we see carboxyl groups previously? We saw carboxyl groups previously when we talked about carboxylic acids. You also have a hydrogen, and then you have this sort of generic letter of R, which represents what is known as the side chain of an amino acid. And what distinguishes one amino acid from the other is that no 2 amino acids have the same side chain. That's the distinguishing characteristic between them. And as you saw, and we'll talk about tonight, the way that amino acids are classified is based on the side chain that they contain. And no two amino acids have the same side chain associated with them. Okay? Now, in water, amino acids exist in what is known as the Zwitter ion form. Instead of the amino group being in the form of NH2, the amino group is in the form of NH3. But now the nitrogen has 4 bonds. So the nitrogen has what charge? The nitrogen has a positive charge. The carboxyl group attached to the central carbon, instead of having the form of C double bond O connected to OH, instead has the form of C double bond O connected to O minus. And then you have your hydrogen, and then you have your side chain. We'll get more into the side chains and Zwitter ion shortly. Essentially, what you have here on the slide is the generic form of what a Zwitter ion looks like. Now, one of the more important points about a Zwitter ion is that a true Zwitter ion is neutral. In other words, at the end of the day, the sum of the charges has to add up to 0. Now, when you look at the generic structure here, you might say, well, wait a minute, doesn't the charge always add to 0? And the answer is actually no. One of the reasons why is that side chains of acidic and basic amino, well, actually, you know what? We'll get to that in a second. Let me take this out there. And let me just say the following. One of the aspects to consider is the side chain. Now, in the Zwitter ion form, the side chain is going to be neutral. But as you saw and as we'll talk about, there are some types of amino acids that essentially, depending on the pH, the side chain may or may not be neutral. Okay, so now we're just focusing on the side chain. But if you have a Zwitter ion, no matter what type of amino acid it is, that side chain has to be neutral. Okay, so for nonpolar and polar amino acids, the side chain is always neutral. Essentially, no matter what the pH is, the side chain for a nonpolar or a polar amino acid is always going to be neutral. Your nonpolar side chains or your nonpolar amino acids have hydrocarbon side chains. Things like methyl, isopropyl, a benzene ring, remember hydrocarbons only contain carbon and hydrogen. So for a nonpolar amino acid, you have a hydrocarbon side chain. For a polar amino acid, you have side chains that contain polar groups like OH, SH, even amide falls into this category as well. Those are the main ones that fall into the category. But again, no matter what the pH is, these side chains are always neutral. However, for acidic and basic amino acids, the side chain is not always neutral. If the acidic or the basic amino acid is in the Zwitter ion form, and again, we'll talk about the isoelectric point, the pH where you have, or the pH range where you have your Zwitter ions. Whether it's an acidic or basic amino acid, that side chain is going to be neutral. But as the pH gets away from that, especially considering physiological pH, around 7.4, neither one of those side chains are going to be neutral. They're going to have a charge associated with it. So, what defines an acidic amino acid? So they have side chains that contain a carboxyl group. So these two amino acids, this type of amino acid actually has two carboxyl groups that are present. The one that's attached to the central carbon and one that's part of the side chain. And the interesting part is that those two carboxyl groups really sort of behave independently of each other. And then for your basic amino acids, they have side chains that contain an amine group. So we know what amine groups are. You have nitrogen that has carbon groups that are attached to them. So your basic amino acids have side chains that contain an amine group. Okay. Now, Zwitter ions exist at a certain pH range known as the isoelectric point, which is usually given as a singular value and abbreviated as PI. Okay. Let's look at acidic amino acids. And the difference with the side chain carboxyl group and the carboxyl group attached to the central carbon. And we're going to look at this in two different scenarios. When the pH is equal to the PI, which means we're looking at a Zwitter ion. And for acidic amino acids, PI is usually like a pH of somewhere around, I think, in the 3s. Okay. And then we'll compare that to physiological pH, 7.4. Okay. Start with the Zwitter ion form first. We know that in the Zwitter ion form, no matter what type of amino acid that you're dealing with, the carboxyl group attached to the central carbon is going to have the form of C double bond O connected to O minus. And again, that's independent of the type of amino acid that you're dealing with. Whether it's acidic, whether it's basic, whether it's polar, whether it's nonpolar, the carboxyl group attached to the central carbon is going to have the form of C double bond O connected to O minus. But what about the side chain carboxyl group? Now again, independent of the type of amino acid, if you're in the Zwitter ion form, the side chain is going to have to be neutral. So the side chain carboxyl group here is going to have the form of C double bond O connected to OH. Because as you know, when you have the oxygen connected, when you have a carboxyl group where you have the OH, that oxygen is neutral. So now the side chain is neutral. And if you put that into here, the side chain's neutral, +1 - 1 adds up to 0. And you have a true Zwitter ion because the overall charge adds to 0. But what about a pH of 7.4? Well, it turns out that the carboxyl group attached to the central carbon stays the same. As you saw in the notes and as we'll talk about, the carboxyl group attached to the central carbon really only changes if the pH gets really, really low, down to about 2 or lower. But what about the side chain carboxyl group? The side chain carboxyl group here also has the form of C double bond O connected to O minus. And because of that, the overall charge of the amino acid does not add to 0. So you don't have a true Zwitter ion any longer. And that, in this case, to me, should make sense to you, because if you think about a carboxylic acid, 7.4 is slightly basic conditions. Can we have an acid under basic conditions? The answer is no. What happens to the carboxyl group under basic conditions? It loses the hydrogen, just as we would expect. Okay. Let's look at your basic amino acids. Okay. So we're going to take a look at two things. We're going to take a look at the amino group attached to the central carbon. And we're going to take a look at the side chain amine group. And again, we're going to look at this in two scenarios. When the pH is equal to PI, which here would be somewhere between 8 to 11 in terms of pH, and when the pH is equal to 7.4. And again, if we're looking at pH equal to PI, we're looking at the Zwitter ion form. Now again, let's start with the Zwitter ion form. Independent of the type of amino acid, if we're in the Zwitter ion form, the amino group attached to the central carbon has to have the form of NH3+. Again, it doesn't matter if the amino acid is acidic, basic, polar, nonpolar, the amino group attached to the central carbon is going to have 4 bonds and a positive charge. But what about the side chain amine group? Well, again, if you're in the Zwitter ion form, independent of the type of amino acid, the side chain has to be neutral. So here, the nitrogen is only going to have 3 bonds. And because the nitrogen is going to have 3 bonds, the nitrogen is going to be neutral. So if the nitrogen is neutral, the side chain is neutral. And now again, +1 and -1 adds up to 0. Now, what about a pH of 7.4? As you saw in the notes, the amino group attached to the central carbon only changes form at very basic pH, like 12, 13, 14. So that stays the same. It's going to stay as NH3. But what about the side chain amine group? Well, at this particular pH, the nitrogen is going to pick up an additional hydrogen. So the nitrogen goes from having 3 bonds to now having 4 bonds. And when nitrogen has 4 bonds, it has a positive charge. And again, now the side chain is going to have an overall charge. So at this particular pH, do you have a true Zwitter ion? And the answer is going to be no. No. For your polar and non-polar amino acids, you have Zwitter ions. At physiological pH. Really, for those, you don't have Zwitter ions when the pH is either very, very acidic or very, very basic. Other than that, essentially, and it could start to change as you go away. Their isoelectric points tend to be between 5 and 6. But at 7.4, they're definitely still in the true Zwitter ion form. All right. Let's take a look at an example. And in reality, the only thing you need from me to draw the structure of a Zwitter ion for an amino acid is the side chain. Because really, everything else stays exactly the same for all the 20 amino acids that you come across. So, in this example, draw the structure of asparagine, where the side chain is the following, and I'll talk a little bit more about this in a moment. At its isoelectric points. Now, the way I give you the side chains, and you saw this in the notes, is that I essentially say R equals, and then I give you the side chain. And the bond that's sort of not directly connected to anything is the bond to the central carbon. Okay? That's the bond to the central carbon. That's there. Okay? So the way I would draw this is I would start with the central carbon. If I'm at the isoelectric point, that means the amino group attached to the central carbon has to be in the form of NH3, where the nitrogen has 4 bonds and a positive charge. The carboxyl group attached to the central carbon has to be in the form of C double bond O connected to O minus. You have your hydrogen, and then you're going to have your side chain. So attached to the central carbon here, we're going to put a CH2 connected to a C double bond O connected to NH2. And that's how I would draw the structure of asparagine at its isoelectric point. And if I were to classify it, the classification would be polar. And the reason I would tell that is because as part of the side chain, what do you have? You have an amide group. And when you have an amide group as part of the side chain, you have a polar amino acid. Okay. One of the things we talked about with the majority of the amino acids that you come across is that the central carbon is chiral. The only amino acid where the central carbon is not chiral is glycine, because for glycine, the side chain is a hydrogen. So the central carbon ends up having two hydrogens attached to it. So it's not chiral. But for all of the other 19 amino acids, the central carbon is chiral. And as you know, for our purposes, if you identify a chiral carbon, that means that the compound is chiral. And remember, what does that mean? That means that not only do you have the version that you're looking at, but there's also a non-superimposable mirror image that also exists as well. And what's the relationship between those two structures? They would be enantiomers of each other. Similar to carbohydrates, amino acids, almost all of them, exist as D and L enantiomers. And can be drawn as Fisher projections. Now, the goal here is not going to be for you to take an amino acid and draw a Fisher projection. But just like we did with carbohydrates, monosaccharides specifically, we want to be able to identify the D and L versions, and using the vertical mirror, we want to be able to draw the enantiomer, the non-superimposable mirror image. Now, essentially for the Fisher projection of an amino acid, you have the central carbon in the middle, the chiral carbon in the middle. At the top, you have the carboxyl group. At the bottom, you always have the side chain. And this is based on the idea that in a Fisher projection, the carbon chain is written vertically with the most highly oxidized group towards the top. The only variation is where the amino group attached to the central carbon and the hydrogen attached to the central carbon are going to be. So when the amino group is to the left, sorry, and it's to the left, brain freeze for a second, you have the L enantiomer. So when the amino group is to the left, you have the L enantiomer. And then on the other hand, where if we were to use a vertical mirror, the carboxyl group stays where it is. Side chain stays where it is. The amino group ends up on the right. And the hydrogen on the central carbon ends up on the left. And this would be the D enantiomer. Okay. So with that being said, if we had the following example, and we said, okay, identify, draw the mirror image, draw the enantiomer for this structure, and identify both as D and L, how would we do it? Well, for the mirror image, we know that for a Fisher projection, when we use a vertical mirror, the vertical groups stay where they are. But the horizontal groups switch. And of course, it would be nice if I actually switched them. That doesn't work well. There we go. That's better. Now going back to the first version, because the NH3 group is to the right of the chiral carbon or the central carbon, this amino acid would be the D enantiomer. And I don't know, quotation marks are really necessary. It's D or L. And for the structure on the right, the mirror image that we drew with the amino group to the left of the central or the chiral carbon, that would be the L. Enantiomer. Okay. All right. I'll take it. All right, so let's talk about amino acids in strongly acidic solutions. And when we talk about a strongly acidic solution, what pH are we talking about? We're talking about a pH of around 2. Okay. So what happens to an amino acid when you get to this very, very low pH associated with it? Well, what happens is that the amino acid behaves as a base, because it behaves as a proton acceptor. Okay, which is a little bit sort of counterintuitive in a sense, because you're in a strongly acidic solution, but the amino acid is actually behaving as a base. In what sense? As the carboxyl group attached to the central carbon accepts a proton. Where's that proton coming from? Well, essentially, how are you making the solution strongly acidic, or when is the solution strongly acidic? If you had a significant amount of acid that's present. That acid that's present, some of it is going to protonate that carboxyl group attached to the central carbon. The bottom line is that no matter what type of amino acid it is, the amino acid now has an overall positive charge. Okay. So the amino acid now has an overall positive charge. associated with it. And again, that would be independent of the type of amino acid that you have. On the other hand, let's talk about amino acids in strongly basic. Solutions, which we talk about essentially a pH of around 13. Now here, the amino acid behaves as an acid because it's behaving as a proton donor. And again, that's sort of counterintuitive because we're in a strongly basic solution, but the amino acid is behaving as an acid. How is it doing that? Well, as the amino group attached to the central carbon donates a proton. As the amino group attached to the central carbon donates a proton. Donating a proton to what? Well, if you think about it, if you're in a strongly basic solution, there is probably a significant amount of OH minus that's present. So essentially, the amino group attached to the central carbon has the ability to donate a proton to the base, where the base essentially has the ability to take off, a hydrogen from the amino group, the NH3, bringing it back to NH2, which we'll talk about in a moment. No matter what type of amino acid that you're dealing with, or you have, no matter what class it is, the amino acid now has an overall negative charge. Okay. And when I say overall negative, and when I said overall positive, in most instances it's +1 -1, but there are some examples. Let me just try to think off the top of my head. If you have which one would be plus? I'm trying to think acidic or basic. Which one would be +2 at that very, very low pH value? Yeah, probably so if you had a basic amino acid in a very strongly acidic solution, the overall charge there would be +2, because not only would the amino group attached to the central carbon have a positive charge, but the amine group in the side chain, that nitrogen, would have a positive charge as well. Now, I don't expect you to know about the +2s and the -2s. And in fact, when I ask you about strongly acidic and strongly basic conditions, I'm only going to focus on polar and non-polar amino acids, because, for basic and strongly acidic and acidic and strongly basic, we'd have to add more to the discussion, make it a little bit more complex, and we won't do that. All right. So let's take a look at an example. Draw the structure of, back for a second, sorry. Draw the structure of tyrosine, which has the side chain of a CH2 connected to a benzene ring, connected to an OH at a pH of 2 and a pH of about 13. Okay. So let's start with the pH of 2 first. So I'm going to start with my central carbon. At this particular pH, The hydrogen atom will be the same as it always has been. And let me just draw that at the top to give myself some more room. For polar and non-polar amino acids, the side chain is going to always be as it is. So CH2 connected to the benzene ring. Make sure you have the right positionings. Look at the OH, right? 1, 2, 3, 4. 1, 2, 3, 4. That's important. But what about the amino group attached to the central carbon and the carboxyl group attached to the central carbon? So at a pH of 2, the amino group attached to the central carbon stays the same as it was in the Zwitter ion form. It's going to have the form of NH3. And because the nitrogen has 4 bonds, it has a positive charge. Okay. What about the carboxyl group attached to the central carbon? Well, at a pH of 2, the carboxyl group is not going to exist as C double bond O connected to O minus. Instead, the carboxyl group attached to the central carbon is going to exist in the form of C double bond O connected to OH. And as you can see, what charge does the amino acid have here? The amino acid has an overall positive charge. Okay. All right. What about a pH equal to 13? Right. So again, hydrogen on the central carbon. For nonpolar and polar amino acids, the side chain is always what it is. But what about the amino group on the central carbon and the carboxyl group on the central carbon? At a pH of 13, the amino group on the central carbon is not going to be in the form of NH3. Instead, the amino group on the central carbon is going to be in the form of NH2. And now, because that nitrogen only has 3 bonds, that nitrogen is neutral. The carboxyl group attached to the central carbon is going to be the same as it was in the Zwitter ion form. It's going to be in the form of C double bond O connected to O minus. But now, does the overall charge add to 0? And the answer is no. Here, the overall charge adds to -1. So at a pH of 2, the carboxyl group attached to the central carbon has the form of C double bond O connected to OH. The amino group stays the same as it was in the Zwitter ion form. At a pH of 13, the amino group attached to the central carbon has the form of NH2. So the nitrogen now has 3 bonds and is neutral. And the carboxyl group attached to the central carbon has the form of C double bond O connected to O minus, just like it was in the Zwitter ion form. All right. All right. It's just about 10:30, so we'll call it an evening. What I'll try to do is we'll have a session, of course, next Thursday, but I'll try to get another one in before. This way we can finish up chapter 16 and then be able to do chapter 17 on the session before the third exam takes place. So I don't know exactly when that'll be, but I'll try to figure out a time and post it via announcement as soon as possible. And I got the chapter 16 homeworks. I'll be grading them this weekend, and hopefully you'll have it back by Monday. All right. Any questions?
No, thank you.
You're welcome. Good luck. Stay well.
Thank you. You too.
Talk to you soon. Thanks.
Bye.
Bye.